Welcome everyone. Let's have a slow start of this second workshop with a brief introduction of myself and the content of this workshop. My name is Gianpaolo Manzolini. I'm professor at the Department of Energy of Politecnico Milano. I work in Initiate project, which is the organizing project together with CORALIS of this second workshop. This second workshop is about CCU modeling approach from micro to macro assessment. So this is a brief overview of the agenda of today. First, there's going to be a brief introduction of the Initiate project by Eric van Dijk, the Initiate project coordinator. Then it's going to be me again about KPIs and modeling overview. Then we're going to go through CORALIS project by Ignacio Julian, who's the project manager, about the techno-economic assessment methodologies. And finally, we're going to go through the micro to final CO2 capture process integration with presentation given by Francesco, Navid, and Nicola. Together with Initiate project, there is also, and CORALIS, there is also C4U project participating to this workshop with Navid Kallagi from University of Manchester. Before we start the workshop, a couple of technical information. The first one, I remind you that this workshop is recorded, and you're gonna be, you can find the recording both on website, and it will be also sent to you via email together with the presentations by the different speakers. You are gonna receive tomorrow an evaluation survey, so to give us your feedback about this workshop, whether you find it useful, and some tips for improving it. Finally, at the end of each presentation, you can have a question time, so you can send the question through the chat, as you are not allowed to speak. Since there are many attendees, we don't want to create confusion and overlapping between different persons. So please text the Q&A in the chat, and I will read them and present to the different speakers. So let's start then with the workshop. Let's start with the first presentation by Eric van Dijk, who is the project coordinator of Initiate, and is gonna present the project with the state of the art and the project's objectives. Eric, over to you.
Thank you very much, Gianpaolo, for your kind introduction. And welcome everybody to this second Initiate workshop. So as Gianpaolo said, I will give you a brief introduction and overview of the Initiate project. If all is okay, you should see my screen now. My name is Eric van Dijk. Indeed, I'm project coordinator of the Initiate project, and this project is coordinated by TNO in the Netherlands, together with 10 other partners. We are executing this program, and I'll say more about that in the presentation. So I'll be giving you an overview of the project, and as an introduction to the presentations that will be coming on the modeling. Okay, so first some words on the concept and the vision of the project. The concept is that we strive for industrial symbiosis between the iron and steel sector and the ammonia and the urea production. So actually utilize the carbon in the off gases of the iron and steel industry as a feedstock for urea, and not only the carbon but also the hydrogen which is in these gases. And we do that by demonstration of the operational reliability to come towards commercial application. And to demonstrate this, we are actually building a pilot, taking in BOF gas and reforming that towards a hydrogen-nitrogen mixture for ammonia synthesis. And eventually, this demonstration, together with the modeling, which we will be talking about in more detail in this workshop, should result in the confirmation of the positive business case for this industrial symbiosis. And this project is done with a consortium of 11 partners, spanning the whole value chain from technology licenses to material and equipment suppliers, end users, and of course knowledge support in the form of universities and institutes. And we also have an external advisory board guiding us throughout the project. So what is this industrial symbiosis about? Here you see the very simplified schemes of a steel plant on the left-hand side and a ammonia and urea plant on the right-hand side. And both of these industries are bulk industries with their own challenge for CO2 reduction. If you consider the iron and steel industry, they typically have a CO2 emission of roughly 2 tons of CO2 per ton of hot rolled coil. And they are actively seeking for reducing their carbon footprint. One of them is change in reductants, so stepping from coal towards natural gas or even hydrogen. Another option would be to implement CO2 capture, and there's a strong tendency of using more scrap, which has a lower carbon footprint. And of course, also the efficiency of steel making is still a topic that is worked on. Then for the urea ammonia industry, it's also very carbon intensive, typically 1.8 tons of CO2 per ton of ammonia. They are also looking at carbon capture technologies, the implementation thereof, but also, of course, the use of green hydrogen towards at least ammonia. But for urea, you would still need a CO2 source. So in this respect, indeed, can symbiosis bring us something if we couple these two industries? And that's illustrated in this slide, where we this is a very simplified scheme of the initiate layout. So what we strive for is that we use part of the BOF gas, so the basic oxygen furnace gas from the actual steel making, and use that as an input for the ammonia and eventually the urea production. Well, a very nice characteristic of BOF gas is that if you remove the CO2, so you shift the CO and remove the CO2, that the hydrogen nitrogen content is very favorable for ammonia production. So that's a very nice link between these two industries. And as you can see, there's two technologies here highlighted in green, which are the enabling technologies in this route, which is the sorption-enhanced shift, which is a reactive CO2 separation technology, and a new approach to the ammonia loop. Okay, so before we started the Initiate project, we did a technical, economical, and environmental feasibility study, which was a one-year project to identify what the potential was for this route. And there, the main results indicate that the techno-economic analysis and the life cycle analysis indicated that this is technically feasible when we use indeed the two enabling technologies from TNO, the sorption-enhanced shift, and from NextChem, the new ammonia loop. There's also positive economic feasibility. Actually, there's a positive business case if you will go all the way to urea, which basically means that the sales of urea would pay for your carbon capture in this scheme. And another really important aspect for the economic feasibility is that we have identified in this pre-study several locations where the BOF gas availability and urea demand is really close to each other. Then on the environmental benefits, that's illustrated on the right-hand graph, where you see these CO2 emissions for the different options. On the right-hand side is the reference case, or reference steel plant together with the reference ammonia and urea plant, which is normalized to 100%. If you then apply the initiate concept, which is the left-hand bar graph, you see that the use of the BOF gas as an input for the ammonia and urea already reduces the CO2 emissions by roughly 15%. And a lot of the CO2 that is removed from the gas is removed as a pure CO2. So if you would combine it with CO2 sequestration, as is indicated in the middle graph, the middle bar graph, you would even go down 70% in CO2 emissions. So there's good opportunities for this route. And a very important aspect of this pre-study is also that we were able to make a strong consortium spanning the whole value chain. So that's when Initiate started up. Actually, Initiate is the follow-up of this project. It's all about the demonstration and the validation of the route and to prepare for the first of a kind plant. Okay, who are the partners involved? These are the 11 partners. We have a 5-year project started in 2020, 21 million euro subsidy from the EU, and we span with this consortium the whole value chain from material and equipment suppliers. TNO supplies the CORALIS technology, NextChem supplies the ammonia loop technology, Johnson Matthey is in there for all the catalysts that we need in these processes, and Consumer Chemicals covers the reactive solvent in our CORALIS technology. Next, there's technology licenses. So again, NextChem and STAMI for STAMI Carbon for the ammonia loop and TNO for the CORALIS technology. End users, 2 very important steel producers in Europe, well, worldwide, I should say, ArcelorMittal and SSAB. And we have knowledge support from the universities and CO2 Value Europe. Okay, so some brief words about one of the enabling technologies, sorbus-enhanced water gas shift. This is a TNO development, and it's based on a solid sorbent that interacts with the CO2 and also has water gas shift activity. So this is a high temperature pressure swing type of absorption separation technology combined with reaction. So in the later presentations, this will be highlighted further. So let's continue. An important aspect of the project is the actual construction of a pilot plant. So in previous projects, we have equipment already in place in the north of Sweden at Swerim next to the SSAB steel plant. And we are utilizing and expanding that equipment towards a multi-column CWAC system and the ammonia loop. But of course, there is a life after this demonstration. So beyond the demonstration, we are focusing on the value engineering and the integration of the different key technologies to reduce the costs of the whole system. And the pre-FEED study should result in a bankable case of a first-of-a-kind plant, combined indeed with site selection, which is an important topic in this project as well. We are also developing artificial intelligence-based control philosophies for the BOF gas to deal with the BOF gas dynamics. And that will also be a topic of one of the presentations, so I won't get to that. And besides these technical aspects, we also focus on social, economic, and environmental impact of this kind of industrial symbiosis in Europe. So where are we currently? We are currently at month 20 of the project, of a total of 60 months, not 54, but 60 months. So what I wanted to highlight here is that we are about to finish the detailed engineering and start the procurement for the pilot. So the layout has been fixed and the control architecture is in development to deal with the dynamics. And on multi-scale modeling, that's in full speed. So focusing on the dynamics of the system to define the plant control. And also the techno-economic and life cycle analysis together with the focusing on the symbiosis is in full speed. And those are actually the topics of today's workshop. So with that, I would like to end this introduction and well, let's continue with the real content. So thank you very much.
Thank you very much, Eric, for your presentation. Before we move to the next one, there is a question from the audience, and they ask whether there is some available publication on the techno-economic assessment and LCA pre-study about initiate process.
Yeah, what we did in the techno-economic analysis for initiate up to now is the definition of the base and reference case, and we are currently working on the integration of the new enabling technologies. On the base and reference case, we have published a well, the deliverable on that is a public deliverable, so you can go to the website and download this public deliverable.
There is also another question: how much BOF gas you can get?
That depends on the steelworks layout. So for this concept, we would like to use as much as possible to go to ammonia and eventually urea. But it of course depends on the energy balance of the steel plant. But preferably as much as possible.
Thank you very much for the presentation. Thank you very much also for taking these two questions. Now we can move forward to the next presentation. So just stop sharing, Eric, please.
How do I stop sharing? Oh yeah, sorry. Yep, sorry.
No worries. So I'll take over from here, and the second presentation is gonna be about actually the first one about the real CCU modeling approaches. Okay, now start sharing, and the title of this presentation is KPIs and modeling overview, how to approach the integration of innovative technologies and define its objective. So as you could see from Eric's presentation, Initiate is going to develop a new concept between the old way to produce steel and fertilizers like urea and try to put everything together. And the idea is to understand what are the benefits of this integrated approach with respect to the state of the art. And this is what we are trying to identify in terms of methodological approach in this presentation. The presentation is going to have 4 main points. The first one is about introduction, then the approach, boundary conditions and definition, and finally, we're going to go through the conclusions. So the introduction is going to be very quick, and it covers why do we need the analysis and the approach. The first aspect is energy transition is going on, and very challenging targets in terms of CO2 emissions are set. So we need to implement new plans and the development of new technologies. This is clear for the last years and is going to be more and more relevant in the near future. Now, when we talk about new plans and new technologies, there are several alternative options which are available. Renewables, where we can cover from geothermal, solar, wind, a lot of them. CCUS, carbon capture, storage and utilization. Again, they can be applied to several different cases, like the cement industry, steel industry, there is nuclear. So a lot of options are available. And we have to identify and define a clear methodology to see which is the most suitable technology to reach the targets in terms of CO2 emissions. Having clear in mind that there is no silver bullet. So we will need all these technologies to reach the CO2 emission targets. Nevertheless, from case to case, we need to identify which is the most suitable one, and we need to identify the most appropriate for different cases. So we have to identify an approach to select the innovative or not even innovative, can be also already available on the market technology for a particular applications. And the selection of this technology shall be based on relevant aspects. And when we talk about relevant aspects, we can list a lot of them. However, the most relevant or the most aspects which are typically considered are, the first one is how much we consume in terms of primary energy per unit of product. So I talk about unit of product because this approach can be extended to power production, to steel production, to urea production, to any conversion process. But there is also the production cost of unit of product. So on top of the primary energy consumption, another criteria which can be considered is an economic criteria. But there is also the environmental criteria which can be considered. And in particular, here I reported the emissions of CO2 per unit of product. Here you have an example because there is the CO2, but there are also a lot of other pollutants which can be considered and accounted when the environmental impact is the main aspect. But there is also technology readiness and input availability, process reliability, like for example, how much the plant will operate over its lifetime, and finally, technology impact on the society. These are just 6, but I can keep on adding other aspects as selection criteria for identifying the most suitable technology. I'm not stating here which is the most relevant or which is the least relevant. I'm just stressing the typical parameters which are adopted as of today to identify the most suitable technologies. And nevertheless, once the criteria is selected, because for example, the final criteria can even be a combination of this list or others, a comparative analysis between all the technologies shall be carried out. So the first aspect, the first approach is to identify which relevant aspect shall be considered for comparing the different technologies. Now, we'll try to move from a very generic approach, which holds for any technology, for any aspect of even our life, and try to go a little bit narrowing down what are the aspects to be considered. And as I started, energy transition is driven by the necessity to reduce CO2 emissions. So the 3 KPIs which I'm going to list now are mainly based on this target, reduce CO2 emissions. And when we talk about CO2 emissions, the 3 targets can be, the first one is the CO2 avoidance. Here, let me use the pointer. Here you have the specific emissions per unit of product of the reference technologies minus the specific emissions per unit of product of the new technology, the one that people want to investigate, like for example, initiate. And the CO2 avoidance is a parameter that indicates how much CO2 emissions are avoided respect to the state of the art, respect to the reference case. So the idea, if we want to reduce CO2 emissions, is to have this parameter in the range of 85% or more. So have a relevant impact in terms of CO2 emission reduction. Another aspect can be the specific energy consumption of CO2 avoided. There is no free meal. If we want to reduce the CO2 emissions, we need typically to consume more primary energy. And this is expressed by the spec parameter, which is the ratio between how much primary energy we consume more to avoid CO2 respect to how much CO2 we avoid. The last KPI, so the first is just about environmental aspects. The second one is energy aspect because it takes into account the primary energy consumption. The last one is the economic one. How much it costs more to produce the same product with respect to the reference technology, respect to how much CO2 is avoided. So this cost of CO2 avoided gives you the idea how much you paid more to prevent the emissions of 1 ton of CO2, for example. As stated, these are the 3 main KPIs to be adopted when dealing with CO2 abatement technologies or even renewable. If you deal with other technologies, other KPIs can be adopted. Very general, now we dig a bit into how these KPIs should be defined and calculated. And I will start defining the boundary conditions, which are very relevant. And the boundary conditions for this case, since we need an example, will be given for the iron production case. Iron production case, which is the one considered in the initiate process. So the product of the steel industry is iron, and the process is here reported. You can see that the process is quite complex since you have several steps, several units. All the arrows indicates mass and energy transfer from one conversion process to the other. Nevertheless, when we do the analysis, when we want to assess the KPI, we have to clearly identify what are the boundary conditions of our analysis. So we have to draw the boundaries where we start calculating the output, which is the product, for example, in this case it is iron, but also the input. Input, which typically are materials, as you can see, it's in kilogram of input per J, so you have multiple materials input and they have to be accounted per unit of time. The energy, which is in megawatt input per J element, because we have different form of energy, electricity, heat, cold, and also as form of fuel. And then we have consumables, so elements which are needed to carry on the whole conversion. But in addition to the input, we have to determine what are the output. Output of emissions, so kilogram of output per K element per second unit, and then also the energy. The idea is that the modeling of the process is needed to determine what are the input and to determine what are the output. Input and output, which are mandatory to calculate the KPIs, which I described above. So here is where heat and mass balance and the process modeling come into place, because we need a detailed model to assess the overall heat and mass balances. Now I'll try to make a few examples for the three KPIs I just introduced. So if we go to the spec, which I remind you is the primary energy consumptions for avoiding 1 ton of CO2. So it's the primary energy consumption of the new case minus the primary energy consumption of the reference case. We need to account between the input and the output mainly about the energy at the input and the energy at the output. What I want to stress is energy input and output shall be reported to primary energy quantity. So when we calculate the spec and we calculate the primary energy consumption, we cannot mix different forms of energy, but we have to go back to the common denominator, which is the primary energy consumption. And here it is an example of how to move from, for example, the input of fuel, the input of electricity, and the input of heat in terms of primary energy. The conversion of these different forms to the primary energy shall be accounted. For example, you need to calculate how much primary fuel was needed to produce the amount of electricity required by the plant. This is just an example. If you go, for example, to remove to the CO2 avoidance, there is the emission of the reference, the emission of the new, so it's straightforward to account for the emission of the plant. But don't forget that also the energy input and energy output has some emissions correlated. So emissions connected to energy sold, purchased, shall be accounted in order to do the overall balance of the system and not just closing the system in itself. Once this is closed and calculated, we can go to the last KPI, and it is the cost of CO2 avoided, which I remind you is the cost of the unit of product with the new process minus of the cost unit of product with the reference state-of-the-art technologies versus the emission saving. Again, to calculate the cost of CO2 avoided, we need the heat and mass balances, because from the heat and mass balances, the size of the component and cost assessment can be done. As an example, the cost of the component is the sum of all the capital expenditure over the lifetime of the plant divided by the product over the lifetime, plus operating expenditure. Example of operating expenditure CAPEX are calculated as a sum of the equipment. So all the pieces of equipment you have to purchase, reactors, heat exchangers, and compressors and so on. And then you have to add all the costs related to installations, contingency, and other costs. While for the OPEX is the sum of fuel, material, consumables, plus minus electricity, because you can even sell more electricity than the one you purchase, so this becomes negative, and have some income from it per unit of product. So these are the three KPIs and how to calculate them, stressing that heat and mass balances are necessary to determine all these aspects, all the single element to determine the KPIs. That's why the following up presentation will show you how to calculate the different components performance and so on, the process performance. In conclusions, the selection of relevant KPIs is the first step to identify the most suitable technology. Here I reported the relevant KPIs for technologies with the aim of reducing CO2 emissions. Modeling of conversion processes is necessary to determine the KPIs. Input and output shall be referred to primary energy consumptions. So we have to go under an homogeneous denominator, which is the primary energy consumptions, and emissions connected to input and output shall be accounted for. So this was the presentation about the main KPIs. So now I'll try to see whether there is any questions. Do you include interest rates in the CAPEX and OPEX calculations? Yes, typically in the CAPEX calculation, you do include the interest because your product in year 1 is more valuable than product in year 20 or 25. And this is how you take into account the interest and the different distribution of the economic income of the process. Why just CO2 cost and not the environmental cost? This is an example. In principle, you can also take into account environmental costs. Nevertheless, the more complex is the parameter you are considering, the more complex and also less accurate the analysis can be. That's why typically try to focus to simpler KPIs. I made an example. When you do the LCA analysis, you have several parameters which gives you an idea about your technology performance. And then it's difficult in the end having multiple parameters, which is the most relevant between the others. And the same goes for the environmental cost. If you have multiple parameters, it's very difficult to identify from the environmental point of view, which is the most relevant and how to assess them. The last question is, being symbiosis, how do you plan to input the cost of CO2 unit to the unit producer or to the ion ore? Thank you for the very good question. Also, the previous two were very good questions. The point is you have multiple approaches. The first one is you have two separate boundary systems. So you allocate the cost to the steel plant, you allocate the cost to the urea plant, and you treat them separately. The other option is, if you consider everything as a whole, you need to fix the cost of the production cost of one product or the other. For example, if you have the symbiosis, you set the steel production cost equal to the reference case, and you recalculate the cost of urea production, or the other way around. Typically, this is the most preferred option because it gives you the idea of the advantage of the symbiosis with less uncertainties respect to have combined analysis with separate boundary systems. I hope I cleared your questions. Thank you very much again for posing them, but we need to move on to the next speaker since we are slightly behind the timeline. So now I give the floor to Ignacio Julian, who is the project manager of the CORALIS project, and he will give a presentation about the techno-economic assessment methodologies carried out in its project. Ignacio, over to you.
Thank you very much. Can you see my screen? Yeah?
Yes, we can see it.
Thank you very much, Gianpaolo, for the nice introduction. Well, first, I want to be clear that I'm not the project manager of CORALIS, but one of the involved managers within CIRSE, which is the organizing and organizer of the CORALIS consortium. So this talk is about the techno-economic assessment of methodologies for the evaluation of the industrial symbiosis actions within the CORALIS project framework. And this is the agenda of my presentation. As most of you are not familiar with the CORALIS project, I will present a project overview. Then I will follow with the industrial symbiosis activities at the demo sites and followers, the 3 demo sites, Escombreras, Brescia, and Fröbi, and CORALIS followers. Then it will be followed by the techno-economic assessment of IS solutions, tools and methods, and 2 case studies. Then price settings in industrial symbiosis actions, and then we will go to final remarks. So, which is the acronym of CORALIS? It is the creation of new value chain relations through novel approaches facilitating long-term industrial symbiosis. As you can see, it's a consortium that holds 28 partners from 7 countries, which has a budget of nearly 20 million euros. And the project itself will last 4 years, from 2020 to 2024. CIRSE is coordinating the project, and as you can see, there are partners from Sweden, Turkey, Italy, Austria, Belgium, and Spain. And the target of the project is first to reduce the primary raw material intensity, then to reduce also the waste generation and the total energy intensity, also reduce by 40% the CO2 emissions, by increasing energy efficiency and giving a better understanding of relevant barriers, effective dissemination of major innovation outcomes, and the demonstration of environmental gains and replication potential. So, as mentioned, we have 3 demo sites, one in Sweden, in the central part of Sweden, which is Fröbi. Then we have a consortium or partnership or 4 industrial sites dedicated to steel and aluminium production in the Brescia region in the northern part of Italy. And then we have the Escombreras Valley in the southeast of Spain. As followers, we have 2 companies, Tüpraş in Izmit in Turkey, Sidenor, which is located in Basauri in the northern part of Spain in the Basque Country. And in Lis, we have 2 merging companies, which are Voestalpine and Borealis, that are the followers of the project. That means that in the 3 demo cases, there will be real demonstration cases of industrial symbiosis, and the followers will learn from the solutions adopted in the 3 demo cases to implement them in a further stage. Starting with the activities of Escombreras Valley, then we have a demo site based in Química del Estroncio, which belongs to the Fertiberia group, which I could see it is an external advisor in the Initiate project. And there is an interaction between this Química del Estroncio, AEMETSA, and Vertex Ecocarburantes. Química del Estroncio is a fertilizer company that produces a sort of fertilizers based on strontium nitrate, strontium carbonate, basically, but also other nitrates as the potassium nitrate, which is a product of interest in terms of the industrial symbiosis that is taking place in here. So we have there at Química del Estroncio suppliers. Also, the Fertiberia group supplies part of their raw materials required for the production of these fertilizers, but we have also interactions with these two companies that I already mentioned within the Escombreras Valley. Then in the case of Brescia, we have Ori Martin, Rafmetal, Torbole, and Feralpi, which are companies dedicated to steel milling, aluminum producing, foundry producing iron products, and steel producers. So this demo case is more similar to what you are considering in the Initiate project, because what they provide is scrap and also dust, metal oxides, silicon oxides, and inner materials out of their main core product that can be valorized again to form pig iron to feed as raw materials 3 of the partners in the company. So the yellowish highlighted units in here in this block diagram represent new technologies or new process units that are being implemented to provide this industrial symbiosis between the 4 partners. And then we have a business-driven industrial symbiosis solution, which is the new generation and relocation of a greenhouse facility to build tomatoes using CO2 coming from the flue gas of a paper and pulp company, as well as renewable electricity from Linde Energy, as well as water from wastewater from the municipality of Lindesberg in the region of Frövi in center Sweden. Okay, these were the demo cases, and then the followers are Sidenor, as mentioned. They want to take advantage of this waste heat in order to store it into thermal batteries and produce steam for themselves, for other industries, but also for district heating in the municipality that is nearby. Then we have Topraz, one of the biggest oil and gas company in Turkey, that has an enormous flow of spent caustic, so ammonia, that can be used for urea production in a nearby fertilizer industry, but also they have a large amounts of CO2 emissions. And since legislation is not that strict in Turkey, that in the rest of Europe, they are planning to adopt CCU as solutions to start reducing from now the production of CO2. Basically, the products, the ammonia and the CO2 could be used in the pulp and paper, leather, paint, or fertilizers industries. And then we have both Talpin and Borealis, which want to envision a renewable exchange option paradigm based on hydrogen production from electrolysis, but also ammonia cracking, as well as methane production via methanation of the CO2 waste of that is generated by both companies. Okay, so let's go to the core of the talk. Well, as any other techno-economic assessment, the assessment of industrial symbiosis actions aims to evaluate the technological feasibility and economic opportunities for industrial symbiosis. So to that end, there is a wide variety of decision tools, which mainly end up in a cost-benefit analysis, as the one that was shown Gianpaolo. So basically, the calculation of CapEx and OpEx of the technology implementation to carry out this technological change. So a complementing methodology, which is already used by companies to detect bottlenecks regarding production irreversibilities and quantify waste production, is this material flow cost accounting. So this methodology establishes a traditional heat and mass balance to the process in a single industry. But it translates the amounts of flows of mass of energy into monetary costs. So this methodology, which in principle was conceived to evaluate the production processes within an industrial facility, can be extrapolated to the industrial symbiosis scenario, in which the blocks in the block diagram represent companies rather than single processes in an industry, so that the waste flows can be accounted for and can be interrelated, interconnected between the companies. In order to evaluate the techno-economic feasibility of the industrial symbiosis solutions, results are synthesized into indicators. So the common economic ones are the net present value, the return of investment, the payback period, etc. But this can be complemented with other KPIs, such the ratio of waste to product price as a result of an industrial symbiosis action implementation. So as such, industrial symbiosis solutions do not only deal with technical developments or material and energy exchange flows, but have environmental implications, but legal and ethical implications as well, that may promote the business upgrade. So all these considerations are merged in what we call the industrial symbiosis readiness level matrix to evaluate the overall maturity of industrial symbiosis actions. And analogously, the price setting of the waste flow exchange between stakeholders does not only depend on the techno-economic aspects, but also on market price, negotiation between stakeholders, earnings versus risk evaluation, etc. So we will talk about them later. Well, as already mentioned, Química del Estroncio is a fertilizers producer based in Spain, which key products are strontium-based salts, as well as potassium nitrate. The current thermochemical process involved in the production of KNO3 is not profitable anymore as a result of the large amount of energy and utilities required to run the process. So in here, you can see with the blue lines, the current production scenario, whereas the ones that imply process upgrades are highlighted in red. Okay, as a result of the adoption of this sulfuric acid from AEMETSA and the CO2 from Ecocarburantes or Vertex Bioenergy, we are promoting the reduction of the raw materials. We're integrating waste flows from the neighboring companies into our process, and we are reducing strongly the use of energy and water in the process. As such, the pre and post CORALIS scenarios in terms of potassium nitrate production were evaluated by means of the mass flow cost accounting methodology, by which the waste flows and byproducts were identified and quantified in monetary units. The evaluation of a sort of KPIs allowed evaluating the impact of the technology. And comparing the OPEX plus the waste cost of both pre and post CORALIS solutions, we see that the KPI indicates that the production by this new proposed technology using waste flows from the neighboring companies is much cheaper or is more beneficial. We have a business case in there. Okay, so this is a clear cases of industrial symbiosis plus process intensification promoted business case. The second case study, which may be of higher interest for you because it involves the use of CO2, is the one at Frobi. So It involves the potential exchange of CO2 via a flue gas upgrade using CCUS technologies from a pulp and paper industry to a newly based in Fruby greenhouse for tomatoes production. So the first thing to do is to identify the flue gas sources from the donor industry. Which process provide which amount and which quality of CO2. I'm sorry for blurring this table, but this is confidential and I cannot show the numbers at this presentation. If you are interested, we can contact us and we can provide them up on demand. So we need to evaluate the average and maximum production values need to be tracked. And the presence of impurities needs to be considered, as you can see here. So NOx, CO, ethylene, ozone, etc. Okay, so the second thing to do is the detailed characterization of the streams. So for example, by evaluating the concentration of impurities or contaminants such CO or NOx along the year. Okay. Are they in a reasonable concentration level? May they be harmful for the operators of the greenhouse in case the flue gas is not upgraded and becomes fed directly? These are the questions that we need to answer. But furthermore, we need to take into account the demand profile of the greenhouse in terms of CO2 uptake. So the demand of CO2 by the greenhouse needs to be analyzed. So how big could be the greenhouse? So that to hold the amount of CO2 that the pulp and paper mill can provide. This is something we need to answer and analyze. Okay, the fourth is the evaluation of the quality requirements for the greenhouse atmosphere, which is the maximum allowable limit of impurities, or analogously, the minimum CO2 flow quality acceptable for the tomato growing greenhouse. Are there other CO2 sources that can complement the flue gas from the pulp and paper mill? This is the case study that we need to evaluate. The fifth point is the matching between the source and the sink. So the matching between what the flue gases can offer in terms of CO2 flow and quality, basically, and the amount of CO2 that is required by the greenhouse, and the daily fluctuation of the demand. And finally, we need to identify the most suitable CCU technology on purpose. So, as all of you may know, there exists essentially 4 technologies to do so: the CO2 capture by absorption in, for example, liquid amines, or adsorption in inactive carbon, followed by desorption to increase CO2 purity and clean the flue gas. We could have also membrane technologies to act as a molecular sieve towards CO2 retention and flue gas cleaning. And finally, the direct utilization without concentrating the CO2. The 2 first options allow balancing the variation in demand at the greenhouse, but the investment cost is quite high. Actually, there is not currently a solution which is both economically and technically feasible or tested for this particular Swedish case. The alternative one is not also commercially mature, this one. So basically, the CCU option may provide CO2 concentrations beyond 99%, whereas the cleaning option would provide just 15% CO2 in a flue gas flow with a variable production rate. So as such, again, the cost of each option needs to be calculated, and the KPIs, such the rate between the CAPEX and OPEX of the selected technology and the resulting tons of CO2 delivered into the greenhouse, need to be evaluated. And finally, back to price setting, CORALIS has identified a series of IS options, which waste flow price definition depends on the value of such a waste. the upgrade cost, the market price of the product, or the direct exchange with no price, as you can see in these columns. So let us analyze 3 scenarios in which the market price doesn't play a role in the transaction. So for example, the supply of water with effluents by pulp paper mill into a biogas company. That company may take advantage of such a wastewater to extract part of the organic load as raw material and send back the wastewater with reduced organic load being at no cost. So the second scenario would be an industrial plant, such for example, Sidenor, one of the followers of CORALIS, which waste heat is delivered to a municipality for district heating. And this exchange is paid by the municipality related to marginal production cost. The third scenario could be a metal processing industry, which waste is processed by a materials provider to bring out new briquettes that the waste supplier pays at the price related to the upgrade cost. So these are 3 different examples in which the market price is not defining the final price of the transaction between the partners. So this brings me to the final remarks. Having in mind this threefold approach, the techno-economic assessment, key performance indicators, and industrial symbiosis readiness level price setting mechanisms, we come to this remarks. So CORALIS is a demo project for the generation of real experiences on the deployment of industrial symbiosis solutions in energy-intensive industries. The complexity of industrial symbiosis alternatives and solutions requires the adoption and adequacy of traditional techno-economic assessment methodologies to assess each individual scenario. The techno-economic assessments assesses the technological feasibility and economic opportunity for industrial symbiosis. But the output represents just one of the factors that determine the industrial symbiosis readiness level. There are other 5 identified factors. Industrial symbiosis transactions are influenced by price-setting mechanisms beyond the techno-economic considerations. So, for example, as said, market price, environmental issues, legislation, negotiations between parties, etc. And the industrial symbiosis solutions involving CO2-rich gases exchange requires thorough characterization of streams, quality, demand production matching, and CCU technologies implementation, if required. So that's all from my side. Thank you very much for attending this.
Thank you, Ignacio, for this very interesting presentation about the CORALIS project and approach. I'll ask the floor whether there is any question. While waiting for a question from the audience, I have a question for you, very quick. In slide 13, when you started to present the first symbiotic case, there was a strong reduction of OPEX. Yeah, this one, exactly, from the first case to the second one. It's less than 50%, the cost of OPEX in raw material and waste. What about the CAPEX? Are they going to change, or is just the process as it is?
Yeah, indeed. We are not considering here in this KPI the CAPEX, because as you can see, not only industrial symbiosis will take place, but also a new technology that is under patent protection will be developed to minimize drastically the use of water, but also the use of energy. It's a reactor based on moving resins, but I cannot say more than that. But of course, yeah, the OPEX, the CAPEX will change higher, and it's important and need to be balanced with the OPEX to develop this final solution.
Thank you very much again for your presentation and for taking this question. As there is no other question from the audience, we can move to the next presenter, which is Francesco Sebastiani from TNO. Julian, you have to, so you have to, great. Francesco, now you can share your screen. And Francesco will start from the micro components modeling to determine the final system heat and mass balances. Francesco, over to you.
Okay, thanks, Gianpaolo. I guess you can hear me and should be able to see my screen.
Yes, everything is okay.
Yeah, so thanks. This presentation will try to go a little bit more on the level of the technologies and components that enables industrial symbiosis assessment and the approaches that we can take to model the same. So I hope you will follow me on this brief, more micro level discussion. First, just to introduce myself, for those who don't know me, I'm a process technology researcher at the gas process technology team of TNO. TNO is the Netherlands Organization for Applied Scientific Research. We are a research institute that promotes both research services and technology development to accelerate the energy transition. And in our team that you see here on the left, we are an international team of scientists, engineers, consultants, and operators, and we work all around gas process technology development, from high-level assessments to actual testing and development of pilot plant for demonstrating the same technologies. You see in the middle a photo of a project that was concluded a few years ago, the FRESMI project, where similarly to initiate, we had used still gases to produce a chemical. In that case, it was methanol. And in that picture, we had just produced the first bottle of methanol that you might see here in the middle. And this to give a bit of background to the discussion we are going to have, and myself. So micro-level modeling of a process. The first thing I think is interesting to ask ourselves is what is modeling and why should we do it in the first place? The way I see it, we have modeling is an activity, an analytical research activity that allows us to generate knowledge. And this knowledge can be used to generate value or reduce risks when we are developing technology. And in research, usually we try to answer a question through the scientific method. So we wonder how something will perform. And we have different approaches to generate that knowledge, and modeling is one of them. But that's also useful when we are developing a technology. And when we are developing a technology, we are trying to solve a problem or take an opportunity in society to generate value. In that case, we want to create a new concept that enables, for instance, industrial symbiosis, or allows to produce a new product. And in that case, what we want to know, the analysis we want to make is understand whether our concept meet the requirements of this value generation, which are set by all the stakeholders. And in both cases, the modeling activity allows us to analyze, and especially in developing technologies, it's also allowing us to reduce the risks. We could just build a concept and try it out, but by modeling, we can make our efforts more efficient. But then why shall we model at a micro level, and what are the relevant aspects to be included? Following the title of the presentation, I try to answer this question, but I think there can be very broad opinions on this. So if you feel like having a different answer, feel free to add it on the chat. As I was saying before, while building a model, well, that's to generate knowledge and to validate a value proposition and reduce risks. But why modeling on a micro level? Well, modeling on a micro level, so on the level of a specific equipment or even a specific product within this equipment, that can help us to improve the accuracy of our model and reduce the uncertainties around the results, as well as reduce the required amount of experimental and plant data that we might need to build the same model. So makes the entire process of increasing our knowledge more efficient. And finally, how can we identify the most relevant process aspects when we start to dive into more micro and micro level? Well, that starts from the research question in the first place. So what experimental condition, what real life situation do we want to be able to predict? And what's the desired accuracy? And that again comes when we are trying to develop a technology from the requirements or including the KPI that were mentioned in the first presentations before. What requirements do we need to meet to verify, to validate this value generation and actually achieve it? So with this introduction, I'll move to an example relevant to the project that was introduced by Eric before, so Initiate, and specifically focusing on the technology, one of the two enabling industrial symbiosis technology that were mentioned before, specifically the COX. And in this case, we start from a problem. So indeed, this is achieve cost-effective CO2 neutral steam making by 2050. And to respond to this opportunity, we make a concept, which is to convert the steel gases via the CX technology to hydrogen and CO2 products that are ready for CCS and CCU technologies downstream. So you see indeed the picture that was also presented before, where we reroute the gas, the residual steel gases of the steel plant to our Initiate plant, where we are able to produce CO2 that can be stored or reuse for the production of chemicals. And going to the micro level, the idea is indeed to evaluate the performance of the unit and the materials that allow this integration. And this can give us information to more accurately predict whether the products we are making are indeed ready for the CCUS and the CCU technologies. And to tell you a bit more information about the CX itself, CX stands for Sorption Enhanced Water Gas Shift, and it's a catalytic sorption technology. Compared to an ordinary water gas shift reactor, there is an additional separation function added on the same material. So on the reference case situation, you would have just the conversion of carbon monoxide to CO2, and later on you will have to separate your CO2 with an additional equipment. Conversely, in the COX, we are able to convert the CO and obtain a hydrogen product while capturing the CO2 on the sorbent that can be later on regenerated and provide us with a pure CO2 stream for either CCS or CCU application. So then, if this is our concepts, what are our requirements to really make this technology applicable? Then, for instance, we can list 3 high-level requirements, which look at the technological performance of the equipment, so its ability to separate the chemical species and convert the CO to hydrogen, and we can measure that through specific KPI for the equipment itself, like the CO conversion, the carbon capture rate, and the carbon purity. But as well, look at the utilities consumption that relates to the OPEX, but also to the energy emissions and to the overall LCA of the system. Looking at the steam and electricity consumption of the technology itself. And finally, the inventory. Else we will have also a requirement of, for instance, how much space this technology needs to occupy to be placed in a certain plant, or how much sorbent can be used to cost effectively operate the system. And yeah, to give a bit more context to this, you see here, for those who doesn't know, pressure swing adsorption system is essentially operated batch-wise in different stages. So we first operate as a water gas shift reaction absorbing the CO2, and later on we have multiple steps where the pressure is changed to regenerate and extract the CO2, and then go back to the higher pressure and get ready to produce again hydrogen. And this is done in multiple columns, so that we can have always continuous hydrogen and CO2 production. Then we would like to know what sizes and mass material balances can allow us to operate the COX according to the requirements, and that's indeed become our research question. The knowledge we would like to achieve through modeling at the level of the equipment itself. So once we know our goal and our requirements, we can start to implement our model and consider what are the key aspects to be of the process that we will like to integrate. But clearly, if we want to know how the CUX performs, we need to have a model that can capture the behavior of the equipment. And one way to do it is to have, first of all, a physical model of the column. A model that is based on the theoretical transport equations and including the mass balance, the momentum balance, the energy balance, and the species balance for the conversions. As well, the mass transport of the species between the gas phase and the sorbent. And this model is in this case semi-empirical. A purely theoretical model of sorbents will start to become more and more detailed and more complex. So in the end, there is a trade-off when modeling on a micro level. At some point, we might rather find more efficient to use experiments to tune our model at a fundamental level, and then obtain a model that is at the same time flexible and light. And once we have this model, then what we can do is indeed generate understanding. In this case, for the CUX itself. For the CUX itself, we can look at the column's performance in various steps. So you see here how the gas species moves along the column for different set of conditions. And this ultimately can give us the performance of the CUX in different applications. You see in this graph an example of different simulation with various pressure levels of the systems, and how the system is performing in terms of separation criteria, the carbon capture rate and the carbon purity, and how it's performing in terms of inventory. This is the amount of gas that is supplied to the system, and essentially the higher the value, the more compact your system will be. And here, yeah, the higher the value, the closer we are to capturing as much CO2 as possible and as purely as possible. And then we can see, for instance, where our optimal pressure will be to run the system. And similarly, we can do the same with the addition of the steam and electricity. What's important then is that the optimal design can be achieved once we iteratively look at the modeling of the micro modeling, so the modeling of the equipment together with the flow sheet, because choices on this level, like the pressure or the steam that we consume, will then affect the macro performance. So there needs to be a continuous exchange of information between how optimized the performance are on a micro level with how much optimized they are on a macro level to achieve the overall plant optimum. And this brings me to my last slide. So just to summarize then the takeaways for this look that we had at the micro level modeling of a technology. First of all, that process model can generate knowledge to validate process concept or reduce risks and costs. Second, that modeling at the micro level, we can increase the accuracy and reduce the required input of the generated knowledge and apply the model as different application. And finally, that micro and macro level modelings needs indeed to go hand in hand to determine the final optimal configuration of the overall symbiotic system. And
thank you very much, Francesco, for the very interesting presentation. I have already two questions from the audience. The first one is, considering that models are getting better and better in the accuracy, do you believe we will always need experiments? Probably we can deal with uncertainty with good control systems.
Well, the fact that models are getting better, I think my personal opinion is that experiments will always be needed to a certain extent, because if we are talking about theoretical model, the more accurate we make a theoretical model, the more complex it will become, and the more efforts is needed to realize that model, making at some point the development less efficient. Another approach could be to have extremely light models, so move completely into the direction of artificial intelligence, black box kind of modeling. But in that case, you will still need experiments to train your model at the beginning. So I think in any case, experiments will still be very relevant in the coming times.
Another question from Sophia is, what softwares do you use for modeling?
That depends on the type of model. When we look, for instance, the model that I presented of the CUEGs, we typically use packages that are good for optimization and solution of partial differential equations, like MATLAB. If more details are needed, then we will look maybe at CFD packages, ANSYS, but that's for really specific problems. And when we look at the integration of the equipment among when we look at the integration in a flow sheet of multiple equipments, we usually use Aspen Plus packages, or equivalent. You can use gPROMS or any of these flow sheeting tools.
Thank you very much, Francesco, for the presentation, for taking the questions. Thank you for the question from Sophia Antonio. Now we can move on with presentation from Navid. Navid is from University of Manchester, and he works in the C4U project, which is similar to Initiate, meaning that it deals with CO2 capture technology in the steel plant, but there is no industrial symbiosis in this particular case. Navid, over to you.
Thank you, Gianpaolo. So
you can see the screen?
Yeah, great.
And it's in presenter mode. You can go.
Yeah, thank you. Thank you for attending the second initiative workshops. I'm Navid. I'm a research associate at University of Manchester. And I'm going to talk about a detailed model of CO2 capture process, which is about definition of a capture process, characteristic, and performance. So this is the presentation outlines. Before jumping into the main topic of my presentation, I'm going to talk about this a little bit about C4U project and research group, because at the end of the day, they are going to pay my salary, so I have to talk about them anyway. And next, I'm going to talk about the different carbon capture technologies and case studies, the base case which we use for C4U project, and the next step would be process modeling specification and techno-economic performance evaluation at the end. So C4U project is funded by Horizon 2020, and it is about demonstration of efficient solid-based CO2 capture technologies for optimal integration into an iron and a steel plant. And it contains 8 work packages. Work package 1 to 6 is about technical development, scientific, business, societal readiness, and public policy activities. And work package 7 and 8 are about the project dissemination, exploitation, and management. The work package 3, it is the work package that I'm involved in, and the aim of this work package is the design of the C4U capture technologies at industrial scale and the assessment of the energy and cost of the integrated process into the steel work plant operation. So this is our team at the University of Manchester. Not all of them are working on the C4U project. And so this is at least a month's difference between these two figures. But I just noticed that I wear the same clothes in all of them. This is how in academia looks like. You don't have time to think about what to wear. So different carbon capture technologies. It is post-combustion, pre-combustion, and exit combustion. And the critical challenges for all different carbon capture technologies are parasitic load, cost-effective oxygen production, mainly for exit combustion, and application to existing plant, not only power plant, and the scale up, and etc. Among all these technologies, amine solvent-based carbon capture is one of the mature technology that can be deployed to existing plants. This is the figure that I took by our recent visit to pilot-scale amine solvent-based carbon capture plant at Translational Energy Research Center at Sheffield. It is, I think, I'm not quite sure, but I think it works for 1 ton CO2 per day, I guess, if I'm not mistaken. And if you're here in the UK, so I really encourage you to visit that center. This is the case study, the base case which we use for C4U project, and the BFG blast furnace gas along with the steam enters to the 1-stage water gas shift, and after cooling down and condensation process, it enters to the absorber along with the solvent, which is MDEA we use in this model. And the clean gas, or it is better to say to decarbonized syngas, exit the absorber after reacting between the solvent and the feed. And the rich amine enters the regeneration. After regeneration, the amine recycled back to the absorber, and the pure CO2, and the purity is 98, more than 98%, leaves the process, and it liquefied at this stage after being pressurized to 78 bar and cooling down to 25 degree. And at the end of the stage, it pressurized to 100 bar degree, which is necessary for storage. And the Aspen Plus used to simulate the sulfur, and this model is equilibrium, and almost full 4 million ton per year blast furnace gas is considered for this process modeling, and steam at 3 bar and 145 degrees provided. And the 1-stage water gas shift we consider in this process modeling because that it is high temperature water gas shift, and medium and lower water gas shift process are not sulfur tolerant process because usually in the blast furnace gas, there is the sulfur component. So this is our assumption to just assume 1-stage water gas shift. So the detailed information about this process and process modeling and techno-economic analysis are available into our recent publication. And I believe that this presentation will be available to all the attendees at the end of the meeting, so that you can just click on this link and go to that directly to that publication. The process modeling specification, there are many assumptions that you have to take into account for example, for capture plant. So the important is the MDEA and water content ratio, which is 25 to 72, and the heat exchanger minimum delta T minimum temperature approach for heat exchanger that are 25 for gas to gas heat exchanger, and 10 for gas to liquid heat exchanger, and 10 for liquid to liquid heat exchanger. For CO2 compression stage, we use multi-compressor, which is 2-stage and with a cooling intercooler, which is at a temperature of 40. And isentropic efficiencies at we considered 80, and mechanical 95% efficiency we assume. And as I said before, the CO2 delivery pressure is 110 bar. And these are the components I used for into the Aspen Plus, and these are the conditions of blast furnace gas. We assume, as I said, that we assume there is no sulfur in the BFG. These are techno-economic evaluation. These are the important parameters to consider for performance evaluation. One is temperature or pressure, which is required for integration to other process. Heat requirement for steam generation. It is for example, water gas heat process and also for regeneration heat duty. And CO2 capture rate, which is very important, and the CO2 capture rate, if I'm not mistaken, should be 95% of the CO2 should be captured, and the CO2 purity is at least should be more than 97%. And CO2 compression as stage for power requirement, we need that power for CO2 compression, and heat duty for regeneration, which I said in this stage before. So 65.8 kilogram per second of CO2 flow rate and 266.8 megawatt thermal output. The thermal output is the lower heating value of the carbonized syngas, which is exit the process from the absorption, result in the 51.2 kilogram CO2 per giga. It should be gigajoule as a specific CO2 emission. Electricity requirement is 33.6 megawatt for this here. The electricity requirement 33.6 is mainly dictated by the power requirement for CO2 compression, and the cost, the MDA unit is the main contributor to the cost, which is 56.6 million euro. And the point is the economic evaluation here is illustration of the capture unit only integration to the steel plant. For example, you can use the carbonized fuel somewhere else, so we are not considered into this presentation. And by considering all these parameters, the cost of CO2 capture would be around 44.3 euro per ton of CO2. Thank you very much, and I'm open for any question if you have. I just try to wrap it up very quickly. So
thank you, Navid, for the presentation and for sharing these insights about your modeling. As of now, I don't see any question in the chat. Do you mind stressing the difference between the CO2 capture rate and CO2 avoided? Since in my presentation, I discussed about CO2 avoided, while here you introduced the CO2 capture rate. So can you explain how it is defined, please?
Okay, so before answering your question, so I have to say something that, for example, we are considering this process for integrated to the steel plant, and the steel plant is different than, for example, the power plant. So, for example, if you implement the carbon capture to the power station, the amount of power production changes. So this is the point. But for the steel plant, for example, you assume that X amount of ton of the steel gonna produce. So that amount of steel doesn't change before and after integrating the carbon capture plant to the steel plant. So in that case, the CO2 avoidance, actually, at least for the cost of CO2 avoidance and cost of CO2 capture is literally the same, because if you go to do your KPI, the cost of CO2 avoidance and cost of CO2 capture would be the same, just because the amount of steel produced is not changed. But okay, just come back to your question. The capture rate is the difference between the amount of CO2 captured divided by the total amount of C in the feedstock. But the CO2 avoidance, as you said, is the difference between the CO2 before and after capture divided by for the CO2 avoidance. It was, I just forgot it.
Unit of product.
Yeah, exactly. Unit of products. Yeah, this is the difference between these two KPIs.
Thank you very much. We have two questions. I will put them together. Kim asks, why you preferred MDA for CO2 capture instead of physical absorption processes. And at the same time, Elisa asked if you considered capturing CO2 at high temperature with solid sorbents.
Yeah, so I have nothing to do for this because this is the project that I worked on, and it is defined that we have to use the MDEA, but this is the pre-combustion, and the MEEA is mainly used for the post-combustion, and MDEA is assumed that to perform better in this case. So that's the reason we use MDEA. And
why not
yeah,
solids? Why not solid sorbents?
Yeah, we can work on that, but the solid sorbent, I think it should be more expensive, and in case of the flow rate we have, and also regarding the maturity and technology and the cost, we believe that the amine MDA is much better than other technologies.
And also because the solid sorbents like CUX were already covered in previous projects by Polytechnic Milano by myself. So
yeah, oh, exactly. Yeah,
a bit of commercial on my side. Thank you very much for your presentations and for joining this workshop, Navid, and for taking the questions. Now we'll go to the last speaker, last but not least, which is Nicola from Polytechnic Milano, and he's going to give you an overview on how to integrate the different technologies and what are the basics behind system integration. Nicola, over to you.
Thank you, Gianpaolo. Do you see my screen now?
Yes.
Okay, perfect.
Go ahead.
So, thank you. Well, I'm Nicola, a PhD student at Politecnico di Milano, and I will talk about the CO2 capture process integration while the final modeling to determine the overall plant KPI. Here, we have the main outlines of the presentation. I start talking a bit about the general plant design criteria, and then I move to integration of CO2 technologies in the overall plant flow sheet. So the steps should be followed, and I talk about at the end of the initiate project and the work made for the initiate project. So for the regarding plant design criteria, very important at the beginning is the definition of the basis of design, to have clear all the assumption and the requirements and the boundary condition of the project and all the equipment and section of the plant. Here then we have some general rules, for example, compression at low temperatures, general rules to be followed during the plant design criteria. Heat exchange between sources that are similar temperatures, and exploit when possible a viable heat in the plant, because it brings many advantages. For example, minimize the consumption of fossil fuels, decrease the primary energy consumption, decreases the CO2 emissions since we reduce the consumption of fossil fuels, decreases the spec, increases the carbon abundance of the system, decreases the cost of CO2 avoidance. So we have an advantage in terms of KPIs that were introduced before by Gianpaolo. Here, when in general, when we integrate, there is the integration of CO2 carbon capture technology, we have to take into account different requirements for the different sections. So as said before, very important is the basis of design to define all the conditions at the inlet of the different equipment section, for example, temperature, pressure, stream composition. After this first step, there is first design and simulation of the plant without the heat integration. Just to have at the beginning, it's very important to have preliminary heat and mass balances. Then this step is followed with the heat integration to minimize the energy consumption using the available waste heat, use, when possible, the decarbonized streams as fuel to produce additional steam if the waste heat is not enough. And well, if point 2 and 3, 1 and 2 are not enough, we have to take into account the possibility to supply heat from with external sources, for example, with fossil fuel. Well, the last step is the calculation of KPIs that allows to compare different plant solutions and understand which one is the best. We have to take into account that there are different carbon capture technologies, as Navid presented before, and so different technology require different energy, have different energy requirements, and so different plant solutions are considered. Main tools used is Aspen Plus, and just on the right side we have like an example of a model of a MEA carbon capture section. So it's Aspen Plus gives the possibility to compute the energy requirement of the carbon capture process. Moving now, we talk about the Initiate process project. As Eric said at the beginning, the Initiate project is based on industrial symbiosis between the urea and the steel industry, so production of urea from the steel gases. At the center of this symbiosis, we have the sorption enhanced water gas shift described by Francesco. And well, as said before, the residual steel gases, composed mainly by CO, CO2, hydrogen, and nitrogen, are treated in the water gas shift and the seaway section in order to produce a stream rich in hydrogen and nitrogen, suitable for ammonia production, that is combined with a CO2 stream to produce urea. The excess of CO2 not used in the urea synthesis can be sent to storage. So, as said, the CWEX technology is the core for the industrial symbiosis. We have to take into account the requirements of the CWEX technology, so the working temperature, the working pressure, and the steam demand of this technology, but also we have to take into account that upstream of the CWEX, we need some one or more, depends on the composition of the streams, water gas shift reactors. And so we have to take into account also for these reactors temperature, pressure, and the steam demand. Here in this slide, I would like to show the work made for the techno-economic analysis of the Initiate process project. So starting from a steel plant on a commercial scale, we have so a viability, well, steel plant of producing more or less 4 megaton per year of steel, and we have a viability of BFG on both gases that usually are the source of the CO2. On the right side, we have the ammonia and the urea synthesis. We have to connect these two different industries. So the core is the CWEX. The CWEX usually works with an inlet temperature of 400 degrees. While the inlet pressure, we have a range. We have to design and decide at which pressure run the process. And usually we have a constraint on CO2 content at the inlet around 5%. Since, well, part of the, we have in the CWEX, as described by Francesco, we have a water gas shift reaction to convert the final CO present at the inlet. In any case, in general, increasing the steam consumption will increase the performance of the CWEX. Since the BFG and BOF from the steel for the steel industry have an high content of CO, we need upstream the CWEX, a water gas shift reactor to convert the majority of CO in CO2 and hydrogen. We have constraint on the water gas shift section in terms of inlet temperature and inlet pressure, and similarly to the CUX, increasing the steam consumption will increase the performance of the water gas shift. Upstream the water gas shift, we need a compressor, since the BFG and BOF gases are at 1 atmosphere. We have to compress them to the working pressure of the water gas shift and the CUX. So here, as we can see, starting from the residual steel gases, we have a production of hydrogen and CO, with a consumption of steam and electricity by the compressor. The hydrogen and nitrogen stream then, before to be used for the ammonia synthesis, should be treated in a metanator in order to convert the CO and the CO2, the residual CO and CO2 present in this stream, to methane, since the CO and CO2 are poisonous for the ammonia reactor. Then, after the metanator, we can compress the hydrogen and nitrogen stream to a pressure suitable for the ammonia synthesis, since this the ammonia synthesis take place at very high pressure. Once we have the ammonia, we can combine with CO2 and produce urea, a fertilizer. The CO2 from the CUX is a low pressure, so before to be used for the ammonia synthesis and for storage, the CO2 have to be compressed. For storage, the final pressure is 110 bar, as Navid said before. And this is, so here we have completed the flow sheet, but we have to take into account that we have to produce steam necessary for water gas shifts and for the CWEX. So first, we can consider the possibility of exploit all these heat exchangers to produce steam, and if not enough, we can consider also the possibility to use some of the hydrogen and nitrogen as a fuel and produce additional steam, since we will have CO2-free flue gases. So here, this is the final flow sheet of the initiate, and it describes the work made for the techno-economic analysis of the initiate project. Here I reported some of the KPI computed for the initiate large scale plant. And we can see the advantages for the initiate respect to the base and the reference case, in which we are producing in all the cases the same amount of urea, but we have a reduction in CO2 emission and a reduction in primary energy consumption for the renewable energy scenario. This means we have a carbon avoidance of almost 85% and a negative spec. We have a negative spec in this case, meaning that we are reducing the primary energy consumption, and we are reducing the CO2 emission. And this is a very important result of the industrial symbiosis. On the other side, on the right-hand side, we have the results in terms of spec and carbon avoidance computed for increasing the electricity intensity of the electricity. So going from a renewable energy scenario in which we have 0 kilogram of CO2 emitted per megawatt hour to 250. As we can see, the spec increases with the increase in the carbon intensity of the electricity, and the carbon avoidance decreases. So just the final remarks of my presentation. Very important, the beginning is the basis of design, because it simplifies all the following steps, since all the assumptions are clear. Aspen Plus is the main tool used for plan simulation and for heat and mass balances. Well, final step is the calculation of the KPIs for the comparisons of the different solutions. And from the Initiate project, it's an industrial symbiosis project. In a renewable energy scenario, we can reach 85% of carbon avoidance with a negative spec. And that's all.
Thank you, Nicola, for the presentation.
Thank
Very
you.
interesting. We already had a question from Manuel. He asked, what is the percentage of CO2 which is sent to CCU, so to the urea plant, against the one that goes to the storage site?
Well, the percentage, the precise number I have to check, but yeah, the majority is sent to storage.
I have to guess it's 70% goes to storage and 30% goes to the urea plant. This is the order of magnitude, Manuel.
Yeah.
Thank you. Don't know if there is any other question. We'll be happy to take any, since all the speakers are with us. You can ask any question from the first presentation to the very last. While I wait for the questions which may rise from the audience, I want to thank all the speakers for taking part in this workshop. I want to thank Antonio and Lara for supporting in the background all the organization and the dissemination event related to this workshop. And I want to thank you all for attending this workshop, which I remind you it was recorded, and together with the presentation made by the speaker, it will be available on the website and circulated to you via mail in the upcoming days. Tomorrow you will receive an evaluation survey, so please take a few minutes of your time to let us know how your opinion about this workshop. General 1, biggest challenge of the CO2 capture technology. Eric, I guess this is over to you. Eric, you are muted. Okay. So I'm going to Ignacio and...
Sorry, Gianpaolo.
Okay.
I'm not sure. Okay.
First Eric and then Ignacio. Biggest challenge of CO2 capture. Go ahead, Eric.
Sorry, I didn't catch the question.
Biggest challenge of the CO2 capture technology.
Technologies.
So
not the societal aspects. The biggest challenge is to
the one in the project, he clarified, Manuel.
Sorry?
The biggest challenge related to Initiate project.
Okay. The biggest challenge to Initiate project. Yeah, that's a good one. What's the biggest challenge? I think one of the dynamics is coping with the dynamics is a big challenge in Initiate. I mean, if you look at ammonia and urea production, typically chemical production, they want to run as steady state as possible. And we have to deal with the dynamics of the gases coming from the steel industry. So on a technical aspect, I think that's the biggest challenge that we're going to demonstrate in Initiate.
Thank you. And in general, what are the biggest challenges of CO2 capture technologies? Eric and Ignacio. First, Eric.
In general, the biggest challenge is the fast scaling up that's required. I mean, CO2 capture is dealing with big streams, with big volumes. And if you want to make an impact, you have to scale up quickly in the coming decades. I think that's the biggest challenge.
Thank you, Ignacio.
Sorry?
I asked
again,
Ignacio.
Again, I subscribe the words from Eric. The need for a steady state operation and the scalability, and still the high capex of the technologies are restricting their put in operation for bigger industrial plants. Yeah.
Okay, thank you very much. I don't know if any other speaker want to add anything. There is a very last minute question. In comparison to micro and macro scale, do you consider using a scaling factor for CapEx? If yes, from where do you get the data? Francesco and Navid, I guess this question can be for you.
Yeah. Okay, so you go first, Francesco, and then.
Yeah, hi. In comparison, yeah, thanks for the questions. The idea from a technical perspective, the idea of modeling on a micro level and gaining semi-empirical model coupled with physical model is that of increasing the accuracy of our prediction. So actually avoiding a scaling factor, but being able to size a full-scale COX plant based on the knowledge of today that comes from a smaller scale demonstration and pilot plants. So the idea is more not to use a scaling factor, but use our simulation platform and to get the data to tune that simulation platform from our laboratories and our demonstration plants operation, like the one we are going to do in Initiate.
But for the CapEx?
And by CapEx, I mean, sorry, by CapEx, I mean, from a technical perspective, being able to predict at higher scale what would be the inventory, the footprint, the amount of steel, which drives the CapEx of the setup.
Okay. Thank you. Navid?
Yeah, so my answer is yes, because I usually use the scaling factor for calculating the cost and CapEx differently. So it is really hard to answer the second part of the question, that from where we can use those scaling factors, but we usually, so you have to, yeah, I get those data from the literature, but the point is you have to figure out what literature you can rely on. So some literature are the simulation, and the results are validated based on the experimental. So they usually show that you can trust those correlation factor they use. And so yeah, but as I said, it is really hard to say from where we can find those type of scaling factors, reliable one.
Thank you very much. I don't know if anybody else has anything to add. From my perspective, as always, I say to my students and the PhD students, thermodynamics is certain, economics is much more difficult to be predicted, and usually has an inaccuracy between 25–30%, which is not good enough at the preliminary stage to compare technologies, which usually has difference in the range of 5 to 10%. So thank you all. Thank you to the speaker. Thank you to the organizer of the event and the support. And thank you all for attending this workshop. And looking forward to see you in further events. I hope you enjoyed this workshop and it was useful.